Okay, everyone, welcome to our afternoon session. I hope you enjoyed your lunch, and let's thank our sponsor, Noah Nidus, for our lunch break. That was very nice of them to provide that for us. Um, okay, so for those of you that did not hear the introduction of who I am, I'm Stephanie Conley. I work for the U.S. Forest Service, the Northern Research Station, our research and development branch. I'm a non-research soil scientist and a liaison to the field. My job is to broker collaborations and partnerships with research and development and managers. I have a special area of emphasis in soil moisture and soil carbon, and a special partner that I work with frequently, the Natural Resource Conservation Service, also with the USDA, as well as in our sister agency within our department of the U.S. Department of Agriculture. Um, I'll be hosting your afternoon session, and we're going to get started here, and we're going to do a panel discussion, change it up a little bit. And with that, we're waiting for our session to our slides to we're good? Okay, we're okay. So with that, I'm going to turn it over to our panel guests. We're going to take about 30, 40 minutes here. We have a little bit of extra time in our afternoon session. We had a few cancellations. And I am going to turn it over to our speakers, and I'm going to go down the row here. Hang in there with me. I'm doing okay this afternoon. Got a little dehydrated yesterday, so hydration's important. Water is important, people, both in the soil and in our bodies. Um, so let's just take a moment and have you all introduce yourselves. And Peter, I'm going to start with you. And I've been a long time collaborator with Peter and have greatly enjoyed working with him. So go ahead, Peter.
Hi, everyone. My name is Peter Goble. I'm a climatologist with the Colorado Climate Center at Colorado State University. And this panel was actually kind of the brainchild of Marina Skumanich, who used to be with Nidus, just left a couple months ago after she read a paper that came out of our office that I was the lead author on in the Journal of Hydrometeorology. And I actually have a couple slides from it here that we can get to in just a minute. But it was looking at the role of soil moisture in water supply forecasting in the Western United States or sorry, Western Colorado, although other folks on the panel have looked at other parts of the Western United States, and just looking at how things can be much more complicated than they first appear. So look forward to delving into that more and seeing what the other speakers have to say.
I'm Elise Osenga. I'm with the Aspen Global Change Institute, and that's an organization that is primarily focused on interdisciplinary collaboration and fostering different resources that come out of it. But I get to do, in my opinion, the fun stuff. So I run a soil moisture network of 10 stations in the Colorado Rocky Mountains. And that network is focused on soil moisture as well as some other met variables. And much like Peter, the last couple of years, I've been delving into a little bit how can these data be used to better understand water supply and forecasting, because that's a really critical issue in our region right now.
Thanks. I'm Paul Miller. I'm the service coordination hydrologist at the Colorado Basin River Forecast Center. That's just a fancy way of saying that I'm the outreach person. I talk and coordinate with stakeholders and researchers in the academic community to improve our forecasts. We use a ton of data in our forecasts, but one gap that we have is the soil moisture parameters and the data that we use for soil moisture. It's all modeled internally. It's not anchored into any observational networks or models that are based on observational data. So it's a little bit of a gap that we're working on to fill and hopefully improve our forecasts going forward.
Okay, Peter, would you like to start with your PowerPoint? Okay, so folks, the way this is going to go is Peter's going to give you a PowerPoint presentation that's going to provide a little bit of background. And then I'm going to go through a series of questions and kind of we're going to have an open dialogue. During that open dialogue, you may want to ask some questions of our panelists, and we'll do our best to get those, either I'll repeat them or bring you the mic or something like that. So motion right now is a little difficult for me. I've got some inner ear issues, but I've got plenty of people that can help me in the audience facilitate that. So with that, Peter, I'm going to give you back the mic. And would you like me just to advance your slides? You go right ahead and drive it, of course.
Yeah. All right. Okay, thanks. So the motivation for this panel, like I said, it's driven by a paper that came out last winter by myself and my boss, Dr. Russ Schumacher, the state climatologist of Colorado. And the motivation for it was the 2020 and 2021 runoff seasons in the upper Colorado River Basin. Particularly, we focused on western Colorado. And here we're looking at a 3-panel plot where on the left-hand side, you're seeing the percentage of normal April 1st snowpack across major river basins in western Colorado. And you can, the April 1st snowpack is kind of like a benchmark for what you might expect throughout the runoff season in April through July. Seasonal stream flow forecasts are much more nuanced than just looking at April 1st, as Paul can certainly attest to. But you expect that the runoff in the coming season will be at least somewhat in line with the snowpack that you got that winter. Now, the middle panel here is showing the forecasted runoff for that season from the National Resources Conservation Service. And you can see that those numbers are lower in each of our major basins in western Colorado, in some cases significantly lower. So in this case, the NRCS was already kind of on to the fact that we would expect lower runoff than what we might think from snowpack alone, largely due to antecedent conditions like what happened with the precipitation prior to the snowpack accumulating throughout the winter and what our soil moisture state was looking at or looking like. But then on the right, you see what the actual observed condition was. And this pattern kind of repeated itself in 2021. In some instances, it was even worse in 2021. And so that really established the motivation here is, are dry soils to blame for these much lower than anticipated runoff seasons? And, can we use the soil moisture data that we've started to collect, be it with in situ sensors or models or satellites, to improve some of these water supply forecasts across western Colorado, as well as other areas of the western U.S. that have struggled to maintain adequate water supply? We certainly saw from our keynote speaker this morning that, Lake Powell, Lake Mead, this is a big issue in the Southwest U.S. And if water providers aren't getting the water supply that they are expecting at the beginning of the season, that can have serious implications for how the water is managed. But then I also thought that looking at just what's going on with soil moisture was kind of an incomplete picture. If we go back to what we saw in 2020 on the previous slide and in 2021, they were also dry springs. So in order to successfully characterize what we would expect from the seasonal forecast, we would need to know about what was going to happen kind of after that April 1st benchmark, or what's going to happen with precipitation, temperature in April, May, June. And so I'm not going to have time just showing these couple brief slides to really get into the methods of this paper. Please do feel free to talk with me about it afterwards. I feel bad that I'm kind of glossing over the methods because you hate coming to a scientific conference and saying, trust me, I did the science. Like, that's not a good way to operate. But we did basically a hindcast of stream flow for all the years from 1980 through 2021 for the 4 major watersheds in western Colorado. So the Yampa River, the Colorado main stem, the Gunnison, and the San Juan River Basin. And by hindcast, I mean it's like a forecast, but we're not using the verification data from that year in our hindcast. So we're basically not cheating. We're just using the data from other years to try to surmise what the stream flow will be in the year that we're hindcasting. These 4 sites that are circled in red are the stream gauge sites we're hindcasting for, and our predictor data came from the SNOTEL sites upstream for the most part, as well as a soil moisture data source that I'll get into in just a minute. But we're looking at, for each forecast, we're using water year to date precipitation and temperature data, as well as snow water equivalent data, But then we made a number of different machine learning forecasts with different inputs included on top of those base data sources. So we made one with volumetric water content from the Western Land Data Assimilations Systems 1 kilometer soil moisture model. We made one using soil moisture and groundwater. And then this FO, that stands for foresight of observations. This is basically how good could we do if we could make a perfect seasonal forecast for what happens beyond that April 1st point. So if we were able to surmise ahead of time based on a great seasonal forecast what we were going to see in temperature and precipitation throughout the remainder of that time period, how well would we be able to do? And then we have a couple variations where we are using both antecedent and subsequent conditions. And so here each column shows the category of data that we are using as inputs, and then the Y just stands for yes in that row or in that kind of model run. Yes, we are using that, or N is no, we are not. And then this is a look at the changes in Heidke skill score over the base, or just the temperature, precipitation, and snowpack data that we got from including these other data sources. And we did not see statistically significant improvement from using soil moisture or groundwater antecedent conditions, but we saw huge increases in skill for if we were able to include what happened over the spring. So kind of discouraging from a soil moisture standpoint, but if we were able to get better seasonal forecasts, we could close a lot of that gap in terms of error. This is looking at the fraction of variance explained for each of these river systems, April through August runoff over these years, 1980 through 2021, for the Colorado, the Gunnison, the Yampa, and the San Juan. The black line shows the percent of variance explained based on the start month of your forecast or hindcast, just with the base inputs, whereas the blue line shows what if you were able to have a really good seasonal forecast. And as we might expect, as you go throughout the season and you're getting more information about what's going on with the precipitation in the snow states, your forecasts improve to the point where, of course, they converge on one, where it turns out that April through August stream flow is a perfect predictor of April through August stream flow. So we do eventually get to that one mark, but then the shading kind of shows the contribution of the seasonal forecast to improving error versus basically all other errors. And so I think one of my points here talking to a soil moisture audience is, yes, even though we may not have been able to find it in this experiment, we know that physically there ought to be a relationship between antecedent soil moisture and runoff. However, you know that whatever that relationship is, it can only close part of this skill gap in the blue, because we know that the skill gap in the gray, that's coming from not knowing what's going to happen in the season to come. All right, just one more slide on results, and then we'll get back to our panel here pretty quickly. This is showing the forecasted percent of average April through August stream flow for each of the 4 basins using just the base variables, volumetric water content plus groundwater, and then foresight of observations plus your antecedent conditions, and then comparing it to observed. And we've got both 2020 on top and 2021 on bottom. And if we look around here for these case studies of just 2020 and 2021, we do see that the soil moisture data made the stream flow forecasts much more accurate. If we just look at, say, the San Juan River, we can see in 2020, we dropped it from just using the base variables, 77% of normal to 61% of normal, much closer to the observed 39. But then, if we include foresight of observation as well, we get very close, 45 to 39. So we close much of that error by including both what happened before and what happened after the snowpack season. And then these improvements by adding soil moisture are even more dramatic in 2021. One of the speakers this morning, I think it was Mike Pilecki, you saw in the slide for the Southwest, that 2021 was an anomaly in terms of having low soil moisture, especially true for Western Colorado. A lot of these forecasts got better when we included soil moisture, but the implications of the broader results of this study were that there would also be years where you kind of get burned by leveraging this relationship. Of course, it might also be that 2021 was an extreme year, and perhaps this kind of relationship is more clear when we have extremes. So just a couple takeaways here. Peak flow forecasts, as long as, they've been pretty accurate, but as long as we have these errors in seasonal forecast, we know we're going to be prone to errors in the water supply forecast as well. So as long as you have errors in your spring weather forecasts, you're going to be prone to errors in water supply forecasts. And then, well, we weren't able to kind of add significant skill to these forecasts by adding soil moisture data from Western LDAS. We know physically that that relationship is there. However, given what we saw with the relationship to what happens after April 1st, we know that we just need better seasonal forecasts to really get the water supply right in our region. So I'm going to go ahead and wrap things up there, but we can get back into our questions. So thanks again, Stephanie.
Thank you, Peter, for that nice presentation. So now, having looked at Peter's slides and having that background and background, I'm going to go to our other panelists and allow you to expand on that and give your assessment.
Thanks. So I'll start by saying if I had like a book club of journal articles I loved, Goble and Schumacher would be really high on that list. It's super readable. So where I kind of fit in relation to Peter's study is a couple of years ago, following that really 2021 gap, I can't overemphasize for people who aren't in the Colorado River Basin how dramatic this gap between anticipated and actual stream flow was, and the number of challenges it caused in terms of meeting water supply. So that April 1st date that Peter mentioned is a really critical date. As a water manager high up in the watershed, you can't wait until June 1st to decide how much water you release for the year, because at that point you're already getting inflow from snow melt. So they have to make their calls around starting April 1st as to whether or not they want to release water in advance of that runoff. Because if they don't release enough, they have problems with dams overtopping and they just have to flood everybody downstream. But if they release too much, then all of a sudden they haven't stored nearly what they need. Their reservoirs don't fill and they can't meet midsummer demand. So that's kind of why that April 1st date is critical. So I had a stakeholder in my area who runs the reservoir there come to me and say, it must be soil moisture, because soil moisture is the buzzword. Can we put a bunch of stations up above our reservoir? And so I had to kind of take a step back and say, we can, but should we? And first of all, there has to be a long enough data record before those stations can even be incorporated in the forecasts. And second of all, we really don't know what that quantitative relationship between runoff efficiency and stream flow and soil moisture is. So what we did agree to do was to use our in situ record, which is flawed, but honestly the best we could find for this, to start to look at what that relationship might be and do some exploratory research. So what we found both in our readings and in our actual work was this, is that there's this sort of like gradient. So on the end of what Peter found, with the exception of these extremely dry threshold years, there doesn't seem to be a lot of improvement from soil moisture. Kind of on the other end of the spectrum, Adrian Harpold and some others did a paper, I think in 2017, where they were looking at SNOTEL data, I believe in Utah. Is Adrian here? Okay, I'm like, before I butcher this, I should check. And what they found was they actually found that forecasts really, really improved when they added this stream flow, this soil moisture data into their forecast, with a couple caveats. So one of those caveats was if they had a nice long 10-year data record. Another caveat was this relationship showed up much more strongly when the snow versus rainfall ratio for precipitation in years when it was either like a really high snow year, then having really high soil moisture change the runoff a lot, or in years where their snowpack was lower in relation to overall percent of precipitation. And so then what we found falls kind of somewhere in the middle of that. For 9 of our stations, we didn't use one of them because it's in an irrigated area that's just wet every year, all year round. So of those 9 stations, 7 of them really didn't have a strong correlation with runoff efficiency. but 2 of them did. I won't say like super strong, but strong enough to merit further consideration. And what was interesting about these 2 sites that actually had a relationship with streamflow was that they were very different. One of them, it makes a lot of sense. It's a loamy soil, so it behaves how you want it to behave. It's our longest data record. It makes sense that one would have a stronger relationship. The other one is located at a lower elevation in the watershed, and it does not have persistent snowpack. So typically, if you're looking at the relationship between your antecedent soil moisture values, in our case, we use November, and runoff, that soil moisture has to be static year round for you to expect to see a relationship. This particular site, it is not static, and yet we still found a pretty decent relationship. And what seemed to be the common factor between these 2 sites was that both of them had a lot of spread in their antecedent soil moisture values. So our kind of key take home is not every soil moisture site is going to be appropriate for understanding runoff. And what you need is either a long data record or a short data record that has a lot of variation in it in terms of those values. So we don't necessarily have an answer in terms of, how do you numerically tie soil moisture into runoff, but it definitely kind of gave us this key take home of 1, it's super complicated and we can't expect a 1-to-1 relationship, and 2, that it's probably worth looking into more deeply in certain ways.
Great, thanks. And thanks, Peter, for these slides, because I think it really sets up the conversation really well. And I think Elise hit on like a lot of the points that make it difficult to incorporate soil moisture data into seasonal water supply forecasts. Um, for our office and for all the river forecast centers throughout the United States, we use the Sacramento Soil Moisture Accounting Model, and you don't need to know the details of the SAC SMA model, but the soil moisture data and the parameters in the SAC SMA model do not correlate really well or readily with soil moisture sensors that you find out in the field. The SNOTEL network has done a really great job of incorporating soil moisture sensors at a lot of their sites. But what we found is that our model is really trying to capture that deep soil moisture data. You really have to get to 3 to 4 feet deep before you start seeing a correlation with our data. And that's not a trivial depth to go and install soil moisture sensors at a spatial resolution that's meaningful. Also, so much of our water supply is dependent on mountain snowpack. The amount of gauges that are located at these high elevations where most of the snowpack is coming from, that's hard to do, right? Because we're not out there, we're not trying to dig into like granite to put soil moisture sensors into that. Our model's just not capturing that. So what we've started to work with some university researchers at Ohio State and other areas is trying to use machine learning methods and data assimilation methods to use soil moisture networks that are out there right now, and also different soil moisture models to come up with modeled soil moisture data that is anchored a bit in reality. We spend a lot of time in the fall tweaking our soil moisture parameters in our model in response to the base flow, because that's kind of the closest thing that we have that we can anchor our soil moisture data to. The shallow depths that a lot of these soil moisture networks have and have long records for don't correlate very well with our model. So we're working with researchers and kind of trying to look at data assimilation methods and machine learning methods to come up with a way that we can quantify the soil moisture data that makes sense for our model, especially in the fall, because that's when we can start giving our stakeholders an idea of if you're going to see an efficient runoff or a less efficient runoff in response to soil moisture data. One thing that we have done in our office, and we have a report up on our website, so it's just cbrc.noaa.gov, is we do have a sensitivity analysis where we looked at the impact soil moisture does have on our forecast. And I really like how Peter framed the results in this study. Yes, soil moisture has an impact. It's not the only source of uncertainty or error. There's lots of stuff out there, right? The amount of snowpack that we're modeling, the amount of precip that's forecasted versus how much is realized, that all goes into making an accurate forecast. And I'll pick on the Airborne Snow Observatory folks a little bit here. There's a lot of stuff out there where it's like, oh, if we use this data, we're going to have 99% accurate forecast. That's not true. We're not going to get to 99% accurate forecasts based on any one source of data or any one data type. But here, like, with soil moisture, here's an opportunity where I think, yes, we can bridge a gap that we have here where we can correlate parameters in our model with some sort of observational based data set and make some improvements in our forecast. We're not going to get to 99% accurate forecast, but we're going to make some incremental improvements.
Okay, that was a really wonderful discussion. I want to take a minute and go to our audience. Are there any questions?
I guess depending on what kind of instrument you're using, most of the dielectric ones obviously don't measure moisture during the freezing season. Um, what kind of complication does this cause, especially since freezing occurs at different rates at different levels of soil?
I can at least start with that. That's one of the reasons why we ultimately gravitated towards using modeled data, at least for our study. I think that there's a lot of room to maybe improve this by using in situ observations, but both the limitations during a freezing season and limitations just based on period of record were things that held us back from maybe making the best use of those SNOTEL sensors that are out there. But definitely an important point that you basically can't use these sensors when they're frozen.
So I would love to hear later in the day if anyone has an answer to that, but I know you are not supposed to trust your data with a dielectric sensor when your ground is frozen, but I wonder if there's like what temperature at which that kicks in. So we have soil temperature at an 8-inch depth. Even at our 12,000 foot elevation site, we really never get too far below freezing. Like it hangs out right around 32. And I haven't seen sudden spikes or drops in our data when we hit that temperature. So I don't really use that winter data, but it exists, and it exists as pretty much like a static value. Typically what's done in the community is to use the November soil moisture values to get around that issue and just assume whatever your November soil moisture value was at the time your soils froze is what you're going to see when they thaw in the spring. We have seen some movement both throughout the month of November and even in January, February, not in every year, but in some years, that makes me a little hesitant to say that November is the best antecedent timeframe to use.
I don't have much to add, just other than I think one advantage to using this data in cooperation with a model is that, yeah, once you do get to some times where you lose data due to freezing or anything like that, that model can kind of help bridge some gaps there. We use our model all the time when stream gauges start to freeze to kind of estimate the flow when the data is not available.
Okay, thank you. I'm gonna jump in here with a question. I want to reflect back to our invited guest speaker and her lovely talk about tribal and water rights and concerns about water resources and tribal lands. With the tribal connection, how are we doing with data sovereignty with relationship to Western rights?
I don't know. It's a really good question. Maybe above our pay grade. I don't know.
Honestly, we try. Sorry. We do get some data from tribes. It's precip data and some streamflow data that they ask us not to share, and we don't share it. We just use it to help with the forecast. That's all in Arizona. Not a lot of snow-driven water supply going on down there, but yeah, we respect the tribes' wishes with what to do with their data. So we just try to be nice, I guess.
Well, being a subject matter and expert in collaboration, it sounds like we've got a lot of work to do there, and we should do that work. Okay, now I'm also going to jump in here. Well, let me go to the audience. Does anybody else have a question that they would like to pose? Okay, I'm going to jump in with the next one. So I sit in the SMAP, our SMAP meetings from time to time, and I am a big in situ person. You know, I'm not there yet on remote sensing data, particularly with forests. So I'm going to ask this question. Can you discuss the challenges of incorporating in situ data versus satellite data like SMAP in Western water supply forecasting? Are there certain scenarios where one is more relevant than the other?
Yeah, that's a really good question. I mean, I'd go back to some of the things I said to Mike earlier that for one, there's the challenge of when your sensors are frozen, can't really use them to get a trustworthy worthy reading on dielectric permittivity. So if you're trying to use in situ data, you have to really look for what was the soil state before things kind of locked in for the season, where with this application at high elevations, you have this building snowpack on top of your sensor. So before that process started, what was your soil moisture looking like? And then for both in situ and remotely sensed data, you have the challenge of period of record, where I think that the longer period of record you have, the better the data are for this type of application. And oftentimes with sensors, at least the SNOTEL sensors, you're looking at a lot of those got installed in the mid 2000s or more recently. And then with satellites, you typically don't have as long a period of record as well. We looked a little bit at potentially incorporating Grace, but again, that was only about a third of our time series. So I think Grace went back to what, 2003, but at any rate, that was one of the limitations. And then certainly being a forest person, you understand there's extra limitations with those satellites in terms of using soil moisture readings in forests, because they're just better designed to handle more agricultural type landscapes where it's very difficult for soil sensors to get readings through the duff layer at the kind of top. It's difficult when you have a lot of forests are very hilly or mountainous. You have these steep terrain gradients, so you don't always get a clean reading of soil moisture. And so that can throw things off as well, not only with the soil moisture reading from the satellite itself, but also what ultimately gets fed into the models based on what we are able to observe.
So this is a question I think about a lot. I would love to be able to use satellite data on a regular basis, but the region where I work, that watershed is extremely complex terrain and highly forested. And typically satellite derived soil moisture data does not match up with what we're seeing on the ground. And I had an incident last year where a water utility manager came to me and he was like, I don't understand what's happening. This map says our soils are super dry right now, but everything I'm seeing is sopping wet. And so I kind of had to explain to him, like, oh, where did you get that data? And so he pulled up the Grace map. And I said, you know, this struggles with our type of terrain. And I directed him to the CBRFC data as a more representative item. But since I'm running an in situ network, I often think about, like, what's our utility when we have 10 points across a landscape? And yes, we've picked representative areas and representative ecosystems, but the soil moisture is so variable. What can we actually learn from single point observations? And so what I come back to is what we're looking at is either process. So what's the relationship between air temperature or rain event intensity and soil moisture, so we can better understand the process as a whole to better understand how our watershed works and how climate might impact our region. And two is time series. You can compare, how does this year look compared to last year? How does this year look compared to a wetter year? But in terms of understanding our basin as a whole and water supply, there's definitely limited utility to using those single point measurements.
Yeah, I agree with everything that Peter and Elise said, and especially when you're dealing with a basin like we do with the Colorado River Basin, where people are moving water around all over the place with regards to agricultural demands and municipal water use. It gets tough to account for the water. Like, I think there was a paper came out years ago that was using Grace data that said Arizona had like millions of acre feet of groundwater, and it was mostly them just kind of moving water around in the state. It wasn't new water. It was I mean, that water could have solved our issues if that was there. But it's really hard to track that water when we're using some of these different data sets, and that's really critical for what we do.
Okay, I'm going to go back to the audience. Does anybody have any questions? Because I got another one. All right. Okay, so in thinking about your work, how do you leverage the National Coordinated Soil Moisture Monitoring Network to support what you do? And if you had a wish of the network, what would it be?
Yeah, I mean, I would just reiterate that, especially as the climate warms and water scarcity becomes an issue, or it already is an issue in the Western US, this is a really important problem. And I think we have a lot of incredibly smart and talented people in this room. And so, what I would lean on the National Coordinated Soil Moisture Monitoring Network for is their expertise more than anything, where, we know that unless we're able to make leaps and bounds in the seasonal forecasting realm, that there is going to be error associated with these April 1 water supply forecasts. But we also saw that there is other errors contributing, and soil moisture likely has some role in that. And if we can be smarter about how we set up some of these networks or leverage satellite and observations and models to tackle this problem, even marginal improvements in these seasonal water supply forecasts are extremely valuable. So, advice on how we can, use these data more appropriately or to kind of better ends in the future would be huge. So that's what I would hope for from the National Coordinated Soil Moisture Monitoring Network.
So I work for a fairly small organization. We have 10 staff. I and my research technician are the only ones working on this project, with a little bit of help that we can borrow from someone who has a background in geology and water, who is just now being added to our staff. So for me, the National Coordinated Soil Moisture Monitoring Network is really just, when I discovered you guys, it was a huge breakthrough for me, because all of a sudden there was a community where I could talk about everything from, this sensor broke, what sensor are you using? Why did it break? Why can't I trust this data? How long do I have to leave them in the ground for before I can consider the data record acceptable? So just really basic fundamental field science questions, all the way to research directions and what are things I haven't even thought about that could potentially be applications for my data, and what do I need to do to get it there? I'm a huge fan of the data quality guide that's coming out. I've been involved in that a little bit, and I'm unbelievably excited for that to be a resource. So if I had a wish for the National Soil Moisture Network, it would just be, if there's some way, I don't know what ideally this would look like, but for more sustained opportunities to continue with relationships, or to ask questions, or to engage with one another throughout the year.
Thanks. And I think I'm in the same boat with Elise. When we're fully staffed, we have 13 people working in our office, and right now we're down to like 8. So, so if you know people looking for a job, let me know. And so I guess my big wish is just time. I mean, I think we need time, and maybe some grad students who aren't in a hurry to graduate, that would like to really dive into our model, dive into this data, and look for those correlations, look for how we can meaningfully incorporate and use this information in our model to add some skill. And I think that's the biggest wish, is time. That's what we need.
So I'm hearing a need for a quarterly collaboration online meeting with Q&A sessions. Yeah, I think that I could take that to the committee, the executive committee, and see what capacity we have for sponsoring something like that. Okay, I go back to the group. Okay, I got a Tyson. I love it. Tyson's got one out there.
Making me walk, Tyson.
This is a great discussion. Thank you all. Wondering about, I guess, on follow-up to Peter's study, what Harpole looked at was doing a 2-step process where you use the soil moisture information to predict the errors in the seasonal forecast rather than to try to make the forecast directly. I just wonder if you all consider that in your process.
Yeah, good point. So I think Elise and Tanya, you did do that, right? Where you were looking at more how does the soil moisture um, explain basically what's left after what you have from precipitation and snowpack. And yeah, I mean that's not what we did, but we, were using that soil moisture data as a variable in a machine learning study where we also had the soil moisture, sorry, we also had the precipitation and snowpack baked into the forecast. And so I think it's maybe what Adrian Harpold and that group did in Utah is a little bit cleaner way to look at it, but either way, you're kind of seeing the influence of what happens if you add versus don't add soil moisture. But good question.
Do you want me to?
I don't have anything else.
Oh, sorry. Misheard you.
Okay, we have an online question. How good is SMAP HydroBlock high resolution soil moisture data at 30-meter scale available currently for 2015 to 2019? Now, if you don't answer that, I have an answer for that. I know someone in the room that does. Okay, I'm going to hand this off to subject matter expert Mike Kosh.
So that question comes from Dematia. So any downscaled products, so if you don't know, and I'll have a presentation tomorrow that I'll now put a slide in there on this. But any SMAP has a real resolution of 40 kilometers. So anytime you're looking at a soil moisture distribution in a landscape, if your characteristic length scales are 40 kilometers, SMAP's probably okay. Trying to do a 30-meter resolution off of a 40-kilometer, you can do the math on that 10, is it 100 difference? 100x difference there. They're really using Landsat data to help downscale that. And some of the sites do very well, especially if you're in a rangeland, if there's not a lot of dynamic range. If you're in Arizona, I could probably tell you what your soil moisture is most of the time and have a pretty good number. If you're in Louisiana, I could probably give you a decent number most of the time. I have seen some good correspondence for certain sites with hydroblocks, and I have seen some very just non-responsive correlate, like zero correlations, because certain sites, it's all about the sites that you have, because the 30, no one really resolves a good 30-meter, well, not no one, but 30-meter resolution products aren't really, they're using landscape as a part of that, the vegetation signal from Landsat. So into the future, we have NISAR that has going to have a 200-meter product. There are some other 400-meter products using MODIS. 1 kilometer products, even SMAP has a 1 kilometer product. It's all about what are they using to downscale. SMAP Hydroblocks uses Landsat. And again, natural environments, landscape helps dictate. You'd use your traditional ecological knowledge. You see some of those beautiful pictures this morning, show you where there's a lot of green. Guess what? There's probably more moisture available. That's one of the things we learn. Where there's a lot of just dry dirt and land, sand, means there's probably not a lot of soil moisture there. So Landsat helps you do that in natural landscapes, but anything in agriculture or anything anthropogenically influenced is problematic for using that as your source for downscaling. NISAR will have a backscatter product on the 5-meter resolution. So you will be getting direct 5-meter data, but that's backscatter, which you need to upscale quite a bit. So 200-meter product is what they're saying they can produce. And some of the other products, when you talk about Cygnus, might have a 4-kilometer product. And anything active is going to have a higher resolution, especially some of the private companies that are going to start producing things. But buyer beware on anything downscaled, you have to look at what is their downscaling methodology and what are the influences on that signal. If it's just vis-IR resolution like Landsat, there's lots of other things influencing that vegetation distribution than soil moisture. So I would not run out and buy a 30-meter product at this point.
Ooh, there's some buyer beware. Okay, now we're closing to the end of our panel discussion here. So I have one last question for you all. Two-part. So where do you think this field is headed into the future regarding improving Western water supply forecasting? And what are some of the key takeaways you'd like the group to know about soil moisture in Western water forecasting or the use of soil moisture?
Yeah, I think one exciting place where this is headed is as long as we're able to maintain some of the in situ records that we have out there. I think especially on smaller watershed scales like what Elise is looking at, we could maybe use in situ data uh, much more readily in order to improve some of these water supply forecasts. And then just the wealth of information out there and the ability to downscale data. It's come such a long way in the last 20 years. I'm excited to see where it goes in the future. And I think we're going to get better at this, especially given the importance of the issue.
Thanks for the plug, Peter. It's exactly what I want to hear. Yes, long-term research matters. In terms of where we're heading, this is maybe more of like what I'd like to see happening than I don't know that we're fully there yet, but I think there's definitely a movement towards comparison across scales. So from the in situ to the model to the satellite or remote sensed. And I think that's going to be really necessary information because each of them serves such a different function. And in terms of what I'd want the group to know is that at least in the community of Western Colorado and the upper Colorado River Basin, and so far as I know, the lower Colorado River Basin as well, there's a really strong public and decision maker interest in soil moisture data. And they're going to go out there and try to start using it whether or not it's appropriate for their purpose, because they're just desperate to better understand anything they can about the droughts we're dealing with. And so the better of a job we can do as a community in letting them know what our data is or is not appropriate for, or guiding them towards tools that are fit for their need, the more effectively we're going to have a great relationship with them going forward, rather than they try it out, get frustrated, and throw it out. So there's an opportunity here right now.
Great, thanks. And I think Elise phrased it well. There is a desperation with our stakeholders with regards to soil moisture and understanding how to use it. Even a few years ago, we had to take some soil moisture data off of our website because people were misusing it and not really understanding what we had up there. So, yeah, there's this need for it. There's a want to invest in it. There's a want to advance the science, and I think it's a place where there's a lot of opportunity to advance the science. It's a gap where I think there's a good amount of room to play and to make significant steps forward in advancing seasonal streamflow forecasts. It's not, we can look at some of these other things like snow states or streamflow measurements, and you're going to make incremental advances, sure. But I think soil moisture is one where you can really get some bang for your buck if you put the time and effort into it.
Excellent. Thank you, panelists. Thank you so much for that conversation. I hope you all enjoyed a little bit diversity in our presentations this afternoon, the way we presented. Let's give the round of applause for our panelists.